Every day, millions of people travel above roads, bridges, skyscrapers, and busy city streets without realizing that another world exists directly beneath them. Hidden below the surface is a vast network of tunnels, underground railways, utility corridors, power stations, water reservoirs, research facilities, and engineering structures that quietly keep modern civilization running. This hidden world is growing faster than ever before. As cities become more crowded, land becomes more expensive, and populations continue to rise, engineers are beginning to look in a completely different direction, not toward the sky, but deep beneath the earth. Today, some of humanity's most ambitious construction projects are no longer visible from above. They are buried hundreds of meters underground. Entire transportation systems stretch beneath mountains. High-speed railways pass silently below oceans. Massive flood-control tunnels protect millions of people from disasters. Gigantic underground power stations generate electricity for entire regions. And in some places, engineers are even designing entire underground cities capable of supporting thousands or even millions of people. Building underground has never been easy. Unlike constructing a skyscraper where engineers can clearly see every beam and every column, underground construction means working inside complete darkness, surrounded by rock, groundwater, unstable soil, and enormous geological pressure. Every meter excavated presents a new challenge. Unexpected faults, hidden rivers, extreme temperatures, unpredictable rock formations. One small mistake can flood a tunnel, trap heavy machinery, or delay a multi-billion-dollar project for months or even years. Yet despite these dangers, engineers continue pushing deeper. The reason is simple. The future of modern civilization may depend on the space beneath our feet. Across the world, underground infrastructure is becoming one of the most valuable engineering assets ever created. Cities such as Tokyo, Singapore, London, Paris, Shanghai, and New York are investing billions of dollars to expand underground transportation networks, utility tunnels, flood protection systems, and massive underground facilities. Some of these projects are so enormous that they can only be understood when viewed from the air or from inside the tunnels themselves. Making all of this possible is one extraordinary invention. A machine so powerful that it can cut through mountains, carve tunnels beneath rivers, and build pathways where no human could ever dig by hand. Known as the tunnel boring machine, or TBM, this engineering giant has completely transformed the way underground mega projects are built. But the TBM is only one part of a much larger story. Behind every tunnel lies years of planning, thousands of engineers, advanced geological surveys, precision navigation systems, and an incredible level of coordination that few people ever see. Together, these innovations have allowed humanity to create an entirely new world beneath the surface, a world that continues to expand every single year. In this documentary, we'll explore the greatest underground mega projects ever built, discover the incredible machines that make them possible, and uncover how engineers are reshaping the future below our feet. Because sometimes, the greatest engineering achievements on Earth are the ones we never see. Behind every tunnel lies years of planning, thousands of engineers, advanced geological surveys, precision navigation systems, and an incredible level of coordination that few people ever see. Together, these innovations have allowed humanity to create an entirely new world beneath the surface, a world that continues to expand every single year. In this documentary, we'll explore the greatest underground mega projects ever built, discover the incredible machines that make them possible, and uncover how engineers are reshaping the future below our feet. Because sometimes, the greatest engineering achievements on Earth are the ones we never see. Beneath some of the world's busiest cities lies an engineering network so vast that it rivals everything built above the surface. These underground mega projects are not simply tunnels. They are entire transportation systems, flood protection networks, utility corridors, research facilities, and underground infrastructure designed to support millions of people every single day. One of the greatest examples is the Gotthard Base Tunnel in Switzerland. Stretching more than 57 kilometers beneath the Swiss Alps, it remains the longest railway tunnel ever constructed. Instead of forcing trains to climb steep mountain passes, engineers created a direct route through solid rock. The result transformed transportation across Europe, allowing passengers and freight to move faster, more safely, and more efficiently than ever before. Creating such a tunnel required years of excavation beneath one of the continent's most challenging geological environments. Every meter demanded extraordinary precision. Every breakthrough represented another engineering milestone. Another remarkable achievement lies beneath the English Channel. Connecting the United Kingdom and France, the Channel Tunnel extends for approximately 50 kilometers beneath the seabed. When construction first began, many experts questioned whether such a project could ever be completed. Two teams of engineers started digging from opposite sides of the channel. Working hundreds of meters beneath the surface, they relied on advanced surveying equipment and tunnel boring machines to guide their excavation. After years of continuous work, the two tunnels finally met almost perfectly in the middle. The final alignment error measured only a few centimeters, demonstrating one of the greatest examples of engineering precision in modern history. But transportation is only one part of the underground world. In Tokyo, one of the largest underground flood protection systems ever built, quietly protects millions of people from seasonal flooding. Deep beneath the city, enormous tunnels connect giant vertical shafts large enough to swallow entire buildings. When heavy rainfall threatens the metropolitan area, millions of liters of water are redirected into these underground chambers before being safely released into nearby rivers. Without this hidden engineering system, entire districts of Tokyo could experience catastrophic flooding during extreme weather. Singapore has taken underground engineering even further. Rather than continuing to build new infrastructure above ground, engineers have developed deep utility tunnels carrying water pipelines, communication cables, power systems, and essential services beneath the city. This approach saves valuable land while making maintenance safer and more efficient. Instead of repeatedly excavating busy streets whenever repairs are required, technicians can access multiple utility systems from within a single underground corridor. Many modern cities are now following the same strategy. London, Shanghai, Seoul, Paris, New York. Each continues expanding its underground transportation and infrastructure networks to support rapidly growing populations. Every new metro tunnel reduces traffic congestion. Every underground utility corridor improves reliability. Every engineering decision helps cities become more sustainable while preserving limited surface space. These remarkable projects share one important characteristic. Most people never notice them. Millions travel through underground stations every day without realizing the enormous engineering effort hidden behind every concrete wall. Ventilation systems continuously circulate fresh air. Power networks supply electricity around the clock. Water drainage systems prevent flooding. Emergency escape passages remain ready for situations that may never occur. Hundreds of sensors constantly monitor structural movement, temperature, groundwater pressure, and tunnel conditions. Everything works together quietly beneath the surface. Each underground megaproject represents decades of planning, billions of dollars in investment, and the combined knowledge of thousands of engineers, geologists, surveyors, architects, and construction workers. Together, they have created an invisible world that keeps modern civilization moving every single day. Yet building these extraordinary projects is only possible because engineers have learned to master one of the greatest challenges on Earth: constructing safely beneath mountains, rivers, oceans, and some of the world's busiest cities without disturbing the world above. And that remarkable achievement begins with a technology capable of making the impossible possible. Every underground megaproject begins long before the first tunnel is excavated. Months, and sometimes years, are spent studying what lies beneath the surface. Engineers cannot simply choose a direction and begin digging. They must first understand the geology hidden deep underground. Teams of geologists drill hundreds of exploration boreholes to collect rock and soil samples from different depths. Each sample reveals valuable information about the strength of the rock, groundwater conditions, underground faults, and possible risks waiting ahead. Using this information, engineers create a detailed three-dimensional geological model of the entire project. This digital map allows them to identify difficult sections before construction even begins. Only after countless investigations is the tunnel alignment finally approved. Next comes one of the most challenging stages of the entire project: launching the tunnel boring machine. Unlike ordinary construction equipment, a tunnel boring machine cannot simply drive onto the job site. Many of the world's largest TBMs are more than 100 meters long and weigh several thousand tons. Every component must be transported separately before being assembled inside a massive launch shaft, specially built for the project. The assembly process alone can take several months. Once every hydraulic system, electrical network, conveyor belt, guidance sensor, and cutter head has been installed, engineers perform hundreds of safety inspections before excavation begins. Finally, the cutter head starts turning, slowly at first. Then, with tremendous force, the giant machine begins crushing solid rock and moving forward meter by meter. Behind the rotating cutter head, conveyor systems continuously remove broken rock, while robotic installation equipment places enormous precast concrete segments around the tunnel walls. Each completed concrete ring immediately becomes part of the permanent structure supporting the tunnel. This entire cycle repeats again and again. Excavate, remove material, install concrete, advance forward, thousands of times throughout the project. Navigation is another remarkable achievement. The tunnel cannot simply follow an approximate direction. It must arrive at an exact destination, often many kilometers away. Laser guidance systems, gyroscopic instruments, satellite survey data, and advanced computer software continuously calculate the machine's position. Even the smallest deviation is corrected immediately. In many projects, tunnel boring machines starting from opposite sides eventually meet with an alignment error measured in only a few millimeters. Achieving this level of precision requires constant communication between surveyors, machine operators, engineers, and project managers. Groundwater creates another major challenge. As excavation moves deeper, underground water pressure can increase dramatically. Without proper control, water and loose soil could flood the excavation face in a matter of minutes. To prevent this, engineers carefully balance pressure inside the machine while continuously monitoring surrounding ground conditions. Hundreds of sensors measure vibration, movement, temperature, pressure, and structural behavior every second. If unusual conditions appear, excavation slows immediately while specialists investigate the cause. Safety always comes before speed. Modern underground megaprojects also operate around the clock. Construction crews work in carefully organized shifts, allowing excavation to continue 24 hours a day. Electricians, mechanics, surveyors, geologists, crane operators, and control room engineers all perform different responsibilities, yet every task must be perfectly coordinated. A delay in one system can affect the entire project. Despite all these challenges, the machine continues moving forward, one meter, then another, until, after months or even years of continuous excavation, daylight finally appears at the opposite end. For everyone involved, it represents far more than the completion of a tunnel. It is the moment when thousands of people, millions of working hours, and decades of engineering knowledge come together to achieve something that once seemed impossible. And once these incredible underground structures are complete, they begin transforming the way entire cities grow and function. Until, after months or even years of continuous excavation, daylight finally appears at the opposite end. For everyone involved, it represents far more than the completion of a tunnel. It is the moment when thousands of people, millions of working hours, and decades of engineering knowledge come together to achieve something that once seemed impossible. And once these incredible underground structures are complete, they begin transforming the way entire cities grow and function. Every year, the world's cities become more crowded. Millions of people move into urban areas searching for better jobs, education, and opportunities. Yet while populations continue to grow, the amount of available land remains exactly the same. This has created one of the greatest engineering challenges of the 21st century. Where can future cities continue expanding? For decades, the answer seemed obvious. Build taller skyscrapers, construct wider highways, develop larger suburbs. But today, many of the world's leading engineers believe another solution may be even more important. Instead of building higher, build deeper. Underground construction is no longer limited to railway tunnels or subway stations. Modern cities are beginning to create entire underground networks that support daily life without occupying valuable surface space. Beneath busy streets, engineers are constructing utility corridors that combine electricity, drinking water, communication cables, district cooling systems, and gas pipelines inside a single protected tunnel. Instead of digging up roads every time maintenance is required, technicians can simply enter these underground corridors and safely access multiple systems in one location. This approach reduces traffic disruption, lowers maintenance costs, and significantly improves the reliability of the system. transportation is changing as well. Many of the world's largest cities now depend on underground metro systems capable of moving millions of passengers every day. Expanding these networks above ground would require demolishing buildings and purchasing expensive land. Building beneath existing cities often becomes the only practical solution. Underground construction also plays an increasingly important role in protecting cities from climate change. Extreme rainfall events are becoming more frequent across many regions. To reduce flood risks, engineers are creating enormous underground storage tunnels capable of temporarily holding millions of liters of stormwater before safely releasing it into nearby rivers. Without these hidden systems, even a single day of intense rainfall could overwhelm urban drainage networks and flood entire neighborhoods. Some countries are already taking underground development much further. Large underground logistics centers, research laboratories, emergency shelters, parking facilities, shopping complexes, and data centers are now operating beneath major cities around the world. These facilities remain protected from extreme weather while freeing valuable land above ground for homes, parks, schools, and public spaces. Technology is making this transformation possible. Artificial intelligence continuously monitors underground infrastructure. Digital twin models simulate tunnel performance before problems occur. Thousands of sensors measure structural movement, air quality, groundwater pressure, and temperature every second. Engineers can identify potential issues long before they become serious. As cities continue expanding, underground engineering will become just as important as skyscraper construction once was. The future of urban development will no longer be measured only by how high buildings rise above the skyline. It will also be measured by how intelligently engineers design the world hidden beneath our feet. Because the cities of tomorrow may not simply grow upward, they may grow downward as well. And the invisible infrastructure beneath our feet could become the foundation supporting the next generation of civilization. And the invisible infrastructure beneath our feet could become the foundation supporting the next generation of civilization. For centuries, underground construction depended almost entirely on human experience. Engineers relied on maps, manual surveying, and countless calculations to guide excavation through unknown geological conditions. Every decision carried enormous uncertainty. Today, that reality is changing faster than ever before. Modern underground mega projects have entered the age of intelligent engineering. Artificial intelligence is becoming one of the most valuable tools on construction sites around the world. Instead of simply reacting to problems, AI systems continuously analyze millions of pieces of information collected from hundreds of sensors installed throughout tunnels and construction equipment. Ground pressure, rock hardness, machine vibration, hydraulic performance, groundwater movement, air quality, temperature. Every second, these systems compare real-time data with thousands of previous construction scenarios. If unusual conditions begin to appear, engineers receive warnings long before serious problems develop. Digital twin technology has become another revolutionary breakthrough. Before a single meter of tunnel is excavated, engineers create a complete virtual copy of the entire project. Every tunnel, every support structure, every utility corridor, every ventilation shaft. This digital model allows engineers to simulate earthquakes, flooding, equipment failures, and emergency situations long before construction begins. Instead of discovering problems underground, they solve many of them inside a computer. Laser scanning technology has also transformed underground surveying. Millions of laser measurements create highly accurate three-dimensional maps of every tunnel. Even the smallest structural movement can be detected almost immediately. This level of precision allows engineers to monitor long-term stability while ensuring every section of the tunnel remains within strict safety limits. Robotics is beginning to change daily operations as well. Inspection robots can now travel through tunnels that may be difficult or dangerous for humans to access. Equipped with high-resolution cameras, thermal imaging systems, and advanced sensors, these machines inspect walls, drainage systems, electrical equipment, and ventilation networks without interrupting normal operations. Some projects are even testing robotic systems capable of assisting with maintenance inside active tunnels. Communication has evolved just as dramatically. Control rooms located hundreds of kilometers away can monitor excavation progress in real time. Engineers receive live updates from thousands of connected devices, allowing specialists from different countries to collaborate on the same project without standing inside the tunnel. Every improvement increases safety, reduces construction time, and lowers long-term operating costs. But perhaps the greatest transformation is not any single machine or software system. It is the way every technology now works together. Artificial intelligence, digital twins, laser scanners, autonomous monitoring, advanced robotics, real-time communications. Combined, these innovations are creating a new generation of underground mega projects that are safer, smarter, and more efficient than anything built before. The tunnels of tomorrow will not simply be stronger, they will also be intelligent. And that intelligence may become the foundation for the next chapter of human civilization beneath the Earth's surface. For thousands of years, civilization has been shaped by the way we build. We built roads that connected nations, bridges that crossed impossible distances, skyscrapers that redefined city skylines, and tunnels that allowed us to pass through mountains once thought impossible to overcome. Each generation solved the challenges of its time by pushing engineering a little further than the generation before. Now, a new chapter is beginning. The cities of tomorrow may no longer grow only upward. They may grow beneath our feet. As populations continue to increase and available land becomes more limited, underground infrastructure will become one of the most valuable resources any city can develop. Future transportation networks may operate almost entirely below ground. Utility systems could be protected from extreme weather. Energy networks may become more reliable. Emergency shelters could be integrated directly into everyday infrastructure. Entire underground districts may eventually support millions of people without changing the skyline above. What once sounded like science fiction is already becoming reality. Around the world, governments are investing billions of dollars into underground rail systems, flood protection tunnels, utility corridors, and research facilities that will serve future generations for decades to come. Every new project teaches engineers something valuable. Every completed tunnel expands our understanding of what is possible. Every innovation becomes the foundation for the next breakthrough. Perhaps the greatest achievement of underground engineering is not the tunnels themselves. It is the confidence humanity has gained from building them. Each successful mega project proves that even the most difficult natural obstacles can be overcome through knowledge, planning, and determination. The hidden world beneath our feet is no longer empty. It is becoming an essential part of modern civilization, quietly supporting millions of people every day. And while most of us will never see these remarkable structures with our own eyes, we benefit from them every time we travel, every time we switch on a light, and every time clean water reaches our homes. The future of engineering will not be defined only by the tallest buildings or the longest bridges. It will also be defined by the invisible world beneath the surface. Because sometimes, the greatest achievements in human history are the ones hidden underground. If you enjoyed exploring the world's greatest underground megaprojects with us today, let us know in the comments. Which underground engineering project impressed you the most? And don't forget to subscribe to Anthill's BuildVerse, because our next journey will take us even deeper into the incredible world of engineering.